Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 121. Water at 20 degrees Celsius of viscosity 0.001 Pascal second flows through an inclined 80 millimeter diameter pipe 30 degrees to the horizontal. At sections 1 and 2, the following data are taken. So pressure at 1 is 186 kilopascals, velocity at 1 or velocity at A 3.2 meters per second, pressure at point 2 260 kilopascals, velocity is 3.2 meters per second, and point 2 is 15.4 meters below point 1. Compute the friction factor, the maximum shear stress, and the maximum velocity. So let's have the figure to serve as our guide in our solution. So this is the figure. Then we first compute for the length. Sine 30 degrees is 15.4 over length. And then we write energy equation between points 1 and 2. Let's assume that the flow direction is from point 1 to point 2 as shown. So L is equal to 30.8 meters. Then we assume that the flow direction is from point 1 to point 2. We write energy equation between points 1 and 2 with datum through point 2. So velocity head at 1, pressure head at 1, elevation head at 1 equals velocity head at point 2, pressure head at point 2, elevation head at point 2, then head loss plus head loss from 1 to 2. So velocity head at 1 and 2 equal, so we can cancel velocity heads. Then we begin with pressure head at 1, which is 186 over 9.81, then plus 15.4 equals 260 over 9.81 plus 0 plus head loss from 1 to 2. From here, we can compute the head loss between points 1 and 2, and it is equal to HF also 7.8567 meters. Then we substitute it into the formula by Darcy-Weisbach. Head loss equals FL over diameter velocity head. So 7.8567 equals F length 30.8 over diameter 0.08, velocity head 3.2 square over 19.62. Then we can compute the friction factor, and the friction factor is equal to 0.03910. Then the maximum shear stress, which is specific weight head loss diameter over 4L, or friction factor density velocity square over 8. So there are two formulas. We will just call maximum shear stress as tau sub O. Then we will use these two formulas to recall these two formulas. So everything is known here. It's everything is also known in this second formula. So tau sub O is 9810 times 7.8567 times diameter 0.08 over 4 times length, or it is friction factor density of water 1000, velocity 3.2 square over 8. So both will give us the same value of maximum shear stress of 50.05 pascals. And the maximum velocity is equal to mean velocity quantity 1 plus 1.326 square root of friction factor. So V quantity 1 plus 1.326 square root of F. So 3.2 quantity 1 plus 1.326 square root of 0.0391. So the maximum velocity which occurs at the center of the pipe is equal to 4.039 meters per second. Problem 122. SAE 30W oil of specific gravity 0.891, absolute viscosity 0.29 pascal second, flows through a long horizontal 120 millimeter diameter tube. At section 1, the fluid pressure is 128 kilopascals. At section 2, which is 6 meters farther downstream, the pressure is 113 kilopascals. If the flow is laminar, estimate part A, the mass flow rate, part B, the Reynolds number, then part C, the velocity 20 millimeters from the center line. So for our solution, we take note that the flow is laminar, and we are given here the difference in pressure, which is equal to specific weight of SAE oil times head loss. So P sub 1 minus P sub 2 equals specific weight of oil times head loss. So we substitute 128 minus 113 equals 0.891 times 9.81 times the head loss. So the head loss is equal to 1.7161 meters. Then we equate this to head loss by Darcy-Weisbach formula, FL over D velocity head. So 1.7161 equals F times length 6 meters over diameter 0.12, velocity head V square over 2G. Then we can set up F V square, where F is 64 over Reynolds number for laminar flow. So F V square is 0.6734. Then friction factor 64 over Reynolds number, velocity square equals 0.6734. So 64 V square equals 0.6734 times Reynolds number. Reynolds number, diameter, times mean velocity, times density, divided by absolute viscosity. So 64 V square equals 0.6734 times diameter 0.12, mean velocity of flow V, density 0.891 times 1000, so 891 kilogram per cubic meter. Then absolute viscosity 0.29 pascal second. From here, we can cancel V, then solve for V here. So the mean velocity of flow is equal to 3.8793 meters per second. Then we can now compute the mass flow rate, which is Q times density, and Q is pi over 4 diameter square times mean velocity. So pi over 4 times 0.12 square times 3.8793 times 891 kilogram per cubic meter. So the mass flow rate is 39.09 kilograms per second. Then the Reynolds number, which is this expression, 0.12 times 3.8793 times 891 over 0.29. So the Reynolds number is equal to 1430, which verifies that the flow is really laminar because this is less than 2000. Then the velocity 20 mm from the center line, V sub R is V sub C, quantity 1 minus R square over RO square. That's the formula. Where V sub C is 2 times the mean velocity for laminar flow. So we substitute. So V sub 20 equals 2 times 3.8793, quantity 1 minus 20 square over 60 square. Radius of the pipe is 60, half of 120. So velocity 20 mm from the center line is equal to 6.897 meters per second.